Hello. We have Andy Dettmer back for this next presentation, where he will be talking a little bit more about water main assessment programs. Andy?
Thanks, Zach. Today we'll be talking about assessing water mains and the various ways to do that, and we'll be focusing in on helping you plan to have confident budgeting for your capital improvement program, as well as O&M budgeting related to water main assessment. So RJN recently introduced water services, and I'm the water service practice lead. Our vision is to partner with our clients to reduce pipeline risk of failure while achieving low life cycle costs. And our strategy in achieving this is by enabling proactive pipeline renewal decisions by completing swift incremental projects that make a significant impact. And we really have four focus areas as far as the challenges that we see with our clients. The first is making sure that we're maintaining regulatory compliance with EPA. Second is understanding and reducing customer complaints related to our system. Third is related to non-revenue water and addressing the different ways to cost effectively reduce non-revenue water. And then finally, focusing on having short and long-term budgeting strategies in order to reduce our risk of failure. So RJN is not new to pressure pipe assessment. Pressure pipe, these are a few of the different locations where we've done pressure pipe assessment projects across the US. First area of focus that we've done in the past is with risk assessment, looking at the consequence of failure and the likelihood of failure of pressure pipe risk. Second is with transient pressure monitoring. Sometimes we have short pressure waves moving through the system that cause damage or failures. We'll talk about that. Third, we've done valve and hydrant assessment to not only geolocate these assets, but to make sure that they're in operable condition or to figure out what needs to be done. Fourth, we've done some leak and gas pocket detection, some cases with CCTV, and this can be done external, internal, tethered and untethered as well. Fifth, we've done some inline electromagnetic structural inspections to look at the weakening of the pipe wall and to determine what repair and rehab should be done. And then finally, we've done some assessment of water meters, which tend to under-register, essentially so that you're under-billing the customer over time. So we'll start with the end, the conclusions. I like to begin with the end in mind. So if I get cut off here, you'll get the end game here at the beginning. First, I want to convince you that pressure pipe assessment, even though it's difficult, sometimes it can be worth the challenge. Second, it's important to weigh the inspection technology selection and the application against straight replacement. Third, there are some quick, small tasks that provide high value. Some of these can be done in-house, and we're happy to help with those if needed. And then finally, the importance of beginning with one critical pipe. And we'll talk about what's involved in addressing one critical pipe and how that can quickly reduce the overall risk of failure in your system. Different pipe, different challenges. What's shown there on the screen is the gravity pipe. This has been RJN's main focus the last several years, and RJN's done a great job of growing the industry and setting the standard in addressing challenges related to gravity sewer as well as gravity stormwater pipes. Over the last couple of decades, the SSES approach, or Sanitary Sewer Evaluation Survey, has been well accepted in the market. Everything from smoke testing to manhole inspections to some focused areas of CCTV inspections to find inflow and infiltration as well as structural defects within the pipeline, and then to prescribe repairs, rehabilitation, in some cases replacement. But this is gravity pipe. These are different challenges. When we're dealing with pressure pipe, we're not only interested in finding where these pipes are leaking, but we're also interested in the stress within the pipe wall and the associated weakening of that pipe wall due to internal or external corrosion. And this is not something you can see with a CCTV camera. And so in a lot of cases, we're also dealing with flexible pipe like steel, concrete bar wrap pipe, PVC. These types of pipes are also susceptible to the stresses in the soil. If there's not adequate backfill around the pipeline, you can have excessive stress and premature failure. So this is what requires advanced tools and analysis to be able to identify the deficiencies within pressure pipe. So I've spent the last several years doing what I call the typical inline inspection project. It's essentially a three-step process. First, contract is signed either with a consultant or a technology company to, quote, inspect the pipe. Once that contract's signed, there's quite a bit of prep work that needs to happen in terms of evaluating different technology, considering whether or not you need taps or access points, what valves are tied to the system, whether they're inline or laterals, looking at different flow rates, addressing issues with traffic control, or periodic tracking points to track the tools as they're moving through the pipeline. Once that prep work's done, the field work can begin, and typically an inspection report is generated. And so some of the challenges with this traditional inline assessment project, again, looking at those three steps, these are some of the challenges that I've seen over the last several years. First is there's often unrealistic expectations of new technology. Sometimes we get really, really excited when something new comes out and we try it and it may not quite meet up with our expectations. Second is incomplete specifications and requirements. Sometimes the guidance to inspect this pipe were written by people who may not understand the full scope or breadth of what needs to be addressed in terms of project risk. And then with the prep work, sometimes this costs more than anticipated after the contract is signed. And sometimes it's a very, very slow process, taking 1 to 2 years to get the prep work done. And it's oftentimes more disruptive to the public and with traffic than anticipated. And then finally, some of the challenges we've seen with the inspection work itself is lost or stuck inspection tools for one reason or another. Pipe failures induced by inspection. I've personally blown pipes out of the ground by manipulating flows and trying to manipulate flows to get inspection tools through the pipeline. Again, this can cost more than anticipated, and sometimes when you get the inspection completed, there's either poor quality data, sometimes there's entire gaps in the data, and sometimes we're not quite sure what to do next. And so we want to be able to address each of these challenges in the planning stage so that we don't get ahead of ourselves. And I grew up working for my dad, who was a plumber and eventually got into building. And one of his favorite ancient principles that he loved to share was this principle. He shared this with me, and I think it applies here. And it says, "For which of you desiring to build a tower does not first sit down and count the cost, whether he has enough to complete it? For if you lay the foundation and are unable to finish it, everyone who sees it will ridicule you." So this is what we want to avoid, and we've got many, many ways to address this. One of the excitements with new technology I mentioned earlier is what's known in the technology industry as the hype cycle, and this concept is applied to many different technologies. Essentially, beginning on the bottom left here, new technology comes out. It's brand new to the industry. People get really, really excited about it, and then you reach this, what's called the peak of inflated expectations. So once people start trying it and have really, really high expectations of it, what often happens is it doesn't quite meet up to those expectations, and the technology enters what they call the trough of disillusionment. And there are several technologies that are on their way up and on their way down, and what we'd like to do is accelerate through this trough of disillusionment to move up to the point where we're productive by understanding what the technology can and cannot provide. When we talk about water main assessments, it's really part of a larger concept that gets used often in the industry called asset management. And there's really two different approaches to asset management. The first approach is what I call a top-down. The second is what I call a bottom-up. So the top-down approach is a higher level view of risk assessment. And RJN's done a great job of applying this on the sewer, storm, and water industry. It's a high level view of the overall risk in your system. It often starts with drawing reviews and GIS mapping, such as this is a water system risk profile we recently completed for a mid-sized utility. And this helped them understand where to focus first and help them prioritize where should they inspect first or where should they replace first based on overall system risk. The second approach is the bottom-up approach. And this is a situation where you're focused on one critical pipe. Oftentimes, a utility knows where that one critical pipe, it's that one critical transmission main or one critical force main that you know if it goes down, there's big, big problems. It's that pipe that has a very high consequence of failure, and it involves doing a deep dive to figure out how to reduce the likelihood of failure of that one critical pipe. And so this not only involves the inspection of the pipe itself, but it also involves looking at the appurtenances. Do the valves work? Do you know where the valves are located? I'm amazed at how many times we just simply can't find the valves because they have not been maintained, and we just haven't simply had the funding for it in the past. Do we know where the fire hydrants are? Do the fire hydrants work? Everything associated with that pipeline and its operation is important. And what we've noticed is each critical pipe has its own story. There's unique challenges to address. There's no one size fits all approach when it comes to addressing one critical pipe. So what are some of the challenges when we think about this one critical pipe challenge? There's really four areas that represent challenges for water mains. The first is regulatory driven. So these are mandates for minimum water quality, water pressure, maintaining fire flows, as well as in some states we're seeing increasing goals or requirements for addressing non-revenue water. The second one with customer complaints. Sometimes we get complaints from customers as the water rates are increased, and being able to make sure that's data driven and justified. We have customer complaints from taste and odor, traffic due to inspection or replacement work, and sometimes repeated disruption if the same street gets shut down year after year due to repeated failures. And the fourth one's kind of a newer one in the last 5 years. We're replacing good pipe. We see this often where replacement programs are driven from a basic desktop assessment, no condition assessment. A lot of the pipe that's coming out of the ground today actually has a lot of life left in it. The third, with data-driven rate increases, one of the challenges here is we've got deferred maintenance that we need to start catching up on. Sometimes it's difficult to justify the budget. Benchmarking against other utilities. AWWA has got some great guidelines around benchmarking. One of the questions I get often is from utilities is, am I capturing the right data? So thinking through what information should we be collecting, and are we collecting some information now that we're wasting time and we're not using it to make decisions? And then finally, risk management through budgeting. How do we manage risk moving forward? And then lastly, who to trust. There's a lot of different people in the market that are offering different technological solutions, software solutions, asset management solutions. And there's a lot of new inspection technologies out there. There's a lot of new repair rehab technologies out there. And in some cases, we see potential conflicts of interest depending on who's offering the products or services. So one of the areas that we help with at RJN is to navigate these challenges. And we'll talk in detail about a few of these. When we focused on pressure pipe, we're going to focus in on some of the technology limitations, repair rehab tech limitations, Sometimes we often have lack of redundancy, lack of access points, and ability to change flows, and thinking through what is this total project going to cost me, and how does that affect my risk profile. So the good news is most of the pipe we inspect's in good condition. There's a paper presented a few years ago at the ASCE Pipelines Conference that reviewed a lot of the previous inspection data for water mains, and it showed that 96% of the pipe inspected is in good condition. 1% has significant damage requiring point repairs or rehab right away, and another 3% has some level of deterioration but may not necessarily warrant replacement or repair today. And this was based on concrete pressure pipe data, both bar wrap concrete cylinder pipe data and pre-stressed concrete cylinder pipe data, PCCP. With metallic pipe, we're seeing somewhat similar results. Approximately 10% we're seeing has distressed or detectable damage within metallic pipe, and the EPA recently estimated that 70 to 90% of the pipe that's being replaced is remaining useful life. So trying to balance this can be a challenge. One of the foundational pipeline risk management equations that gets applied to pipeline risk is a simple one. It's tomorrow's risk of failure is equal to today's risk of failure minus your risk mitigation and contingency plan. So it's a fairly basic equation, but sometimes can be challenging to figure out where to focus first. And so what we've done is broken it down to the 3 options that we see utilities utilize in terms of managing their pipeline risk. And the first one, we call it the do nothing approach. Your overall risk is increasing tomorrow because today's risk is undefined. We know it's increasing, and sometimes we're stuck in that reactive firefighting mode. We're not quite sure where to start. Most utilities, I'd say, are in option 2 with a basic risk reduction program. Their overall risk is still increasing, maybe not quite as fast, because some of their risk has been defined. We'll talk about how to do that in a second, but their overall risk is still increasing, and they do have some type of basic risk reduction program in terms of replacement or assessment to address leaks or structural failures. But lastly, this is where we see a lot of utilities moving, which is option 3, which is a proactive program to at least maintain their current level of service for their customers in terms of main breaks and maintaining good water quality and fire flow. So even though their risk of pipe failure may be increasing today, they do have a well-defined risk profile and understand where they need to focus for their advanced risk reduction program through risk mitigation and contingency planning. So we'll talk a little bit more in detail about how do we define risk and reduce overall pipeline risk of failure. So the first question is, where can I cost effectively reduce my risk? And if we think about today's risk of failure, we can break it up into 3 areas: assumed risk, defined risk, and undefined risk. And we'll dive into that in a second. But I wanted to focus first on the risk mitigation and contingency planning. Risk is defined as the consequence of failure times likelihood of failure. And each one of these can be further broken down as far as strategies with your capital budget, O&M budget. So let's look a little closer at likelihood and consequence of failure. So this falls under the risk mitigation and contingency plan. Likelihood of failure is on the left, consequence of failure is on the right. If we look at how to reduce likelihood of failure, this can be a proactive maintenance program, not only of the pipeline, pumps, and appurtenances, but it can also be following up with proactive repairs. And sometimes those repairs can be driven by your maintenance program, leak detection, proactive condition assessment can drive that repair work. Depending on the decision logic that's applied, you may decide a certain number of repairs or a certain amount of damage from your assessment may warrant rehabilitation or straight replacement. And then also a pressure correction program. We're starting to see more of these with different utilities addressing surge within their system, water hammer, either from the pumps, check valves, or operations of the system, as well as in some cases reducing the overall operating pressure, where you've got very, very high operating pressures. There's been several studies that show by making some small changes, like dropping the pressure by 5 psi, can have a dramatic positive effect on reducing your water loss. Moving to ways to reduce your consequence of failure. One of the easiest things to do is to start a valve maintenance program or enhance your valve maintenance program. This is important for when you have a main break. If your crews know exactly which valve to go to, and they're confident that when they get to that valve, they can find it, and they're confident that it's operable and that it does seal, you can get that water main break shut down very quickly and limit any flooding or damage that's occurring from that water main break. Having an optimized emergency response plan, making sure that you've got the crews available or a contractor on standby, you've got extra pipe fittings, any tools needed to address a water main failure. The quicker you can get that water main back into service, the quicker you've reduced your consequence of failure. There's different failure warning systems out there. Some people call this monitoring, either monitoring pipe degradation or monitoring pressure or pressure drops, in this case, to let you know exactly where the main break occurred and or where the deterioration continues to happen. And then finally, increasing redundancy if it's feasible to put in a second pipeline or have the ability to feed an area from another water source. This can also reduce consequence of failure. Just a quick sidebar on valves and the importance of valves in reducing consequence of failure. This was a surprising statistic to me, is that 40% of valves are not usable. This is based on about 1 million valve data set in the United States, which shows that really only 60% of valves are usable. So what do we often find? About 15% can't be located, about 10% are buried or paved over, about 9% are in the wrong position, meaning they're either partially closed or closed and they should be open, creating water quality concerns. And then about 6% are broken or they need some type of minor rehabilitation to get them working. So addressing these quickly, again, can reduce your consequence of failure. And we like to think of valves not necessarily as only valves, but we think of them as control points. If these are sources of control, if you don't know where your valves are, if they don't work, you don't have nearly as much control over your system as you could. So going back to our fundamental risk equation, we asked the question, how can I better define today's risk? So dealing with this middle column here, how can we better define this risk that we have today in the system? And one of the ways we do that is with proactive field assessments. Once we understand what we have in the field, whether these be over the surface or in pipe, this helps us better define that risk. In some cases, building a risk model, because field data collection can sometimes be expensive. Sometimes it makes sense to start with a basic risk model and then to make it more sophisticated over time if it warrants. But in that risk model, there's going to be a certain amount of risk that's assumed, and that's okay. But we just have to acknowledge that there is some risk that is unavoidable. Even if you put in a new pipeline, you're not guaranteed to have 0 failures, and we are seeing some pipelines, even new pipelines, fail either because of rapid corrosion or poor construction. So how do we get there? One of the important places to start here is to understand what are the different ways my pipe can fail. We have to define our failure modes before we can build a risk model or before we can initiate these proactive field assessments. So we'll spend just a little bit of time defining failure modes and what that means for water mains. So how can my water mains fail? There's really 3 main areas. You can have insufficient capacity. That's a type of failure. Non-revenue water is a type of failure, but usually when people hear failure, they think of a break. And a break is different than a leak, and we'll address that in a second. But with insufficient capacity, a lot of times in these low pressure, longer transmission mains, we'll see gas pockets causing flow restrictions. We'll see other blockages due to sediment, tuberculation, or sometimes the pipe's just too small. And we can address this through looking at hydraulic models. If we do confirm the pipe is just too small, sometimes it makes sense just to upsize that main or put in a parallel. With non-revenue water, there's several different areas here to address. The first is leaks, lots of different sources of leaks. We'll talk about that in a second. Could have theft. We do see that here in the US. There's issues with meter accuracy, as well as billing and other policy decisions within the utility to address what water you're charging for and who doesn't pay for water. And then with breaks, there's really three main areas for breaks: weakening of the pipe wall, internal pressure causing breaks, as well as excessive external loading causing breaks. So we'll break each of these down just a little bit further. So we'll separate the breaks into each one of those three categories. So if we take a step back and look at how these fail, we talked about the insufficient capacity with gas pockets, other blockages, or doing hydraulic modeling. The pipe is too small. We do address issues with odor, and this is really more related to force mains, addressing air valve issues, but we do see air valve issues in water mains, typically causing the gas pockets. Broken out leaks with surfacing and non-surfacing or undetectable leaks. We'll dig into each one of these in detail, the different types and technology to find these different types of leaks. With external loading, sometimes reviewing the design or taking a look at the installation practices to make sure that the pipe is in the right location in terms of bury depth. And with increased overburden, we're looking for areas where additional fill has been added on top of the pipe, either from developers in the area, changing the overburden, or say Department of Transportation or somebody building roads, or changing the fill on the pipe causing excessive loading. With internal pressure, we're looking to make sure that the pipe was designed or installed and designed properly. But most of the time we're addressing surge events that sometimes can be mitigated. And a lot of times this is an issue at the pump station, check valves, or operations within the system. And then lastly, pipe wall weakening, talking about different technologies to detect corrosion, both internal corrosion, external corrosion, or depending on the pipe type, wire breaks or bar breaks within the pipe wall. But then acknowledging that there are there's no one technology that tells you everything you want to know in terms of pipe wall weakening. So there is some damage that is undetectable that provides some risk of failure in the future. So what does our toolbox look like when we want to reduce our pipeline risk of failure? And so thinking about each of the five categories, what can we bring to bear to address these challenges? So with insufficient capacity, it's typically starting with a drawing review, looking at the hydraulic grade line to figure out what should we be getting from this pipe. Then it can move out into the field, looking at air valves, maybe doing some pressure drop sampling to see where these restrictions are occurring, perhaps some hydraulic modeling to figure out, is this pipe undersized? And then in red, taking the extra step of maybe doing inline acoustic inspection to find gas pockets, and inline visual inspection as well. With leak detection, trying to find leaks, again, starting with a basic drawing review, hydraulic grade line to understand what pressures that you're dealing with, walk the alignment. It's amazing how many times I've walked alignments with utilities, and we're surprised when we find a big leak that was surfacing. We just didn't just wasn't aware it was there. So just walking the alignment can be an easy way to find big leaks. Applying external acoustics can sometimes be effective. There's some newer technology using drones or satellites to detect leaks. That is a possibility. We're kind of in the process of evaluating how effective that is. Internal hydrophones to listen for leaks, and then finally applying some type of inline acoustic tool or district metered areas or DMAs to figure out what parts of the system are the most leakiest to focus this work. With external loading, looking at drawing reviews, making sure that it was designed per AWWA standards, walking the alignment to see if there's any big things that have been built over the pipe recently. Again, we're surprised at what we find sometimes just walking the alignment. Perhaps doing a LiDAR survey to figure out how much overburden we actually have. In some cases, potholing if we're uncertain of the invert depth with the survey. And then finally, in some cases, doing a finite element analysis to figure out how much stress can this pipe actually take before we're concerned about failure. With internal pressure, again, looking at the drawings, hydraulic grade line, talking to the operators to figure out how this pipe gets operated, particularly with the pumps. And if you have any large customers downstream pulling water off the line, sometimes this can be a source of surge. Walking the alignment, looking at the pump station, doing some transient pressure monitoring, hydraulic modeling, in some cases doing some pump testing if there are issues. And in some cases, making some modifications or improvement to reduce surge pressure. And then finally, pipe wall weakening. Always want to start with a drawing review to figure out if you know what you have. Sometimes we're surprised there's been portions of pipes that have been relocated. Talking to the operators who've been working at the utility for a long time and inquiring about old repairs that have been done. What's the break history? What kind of soils do you have in the area if external corrosion is of concern? In some cases, doing high resolution spot checks using various tools to get detailed information at the high risk areas. There's some technology that utilizes pipe wall averaging. I have a question mark there just because we're still evaluating the efficacy of that technology and how to apply it. But it can be a great tool from the outside. In some cases, going inside, doing visual assessments, laser or sonar profiling if it's a flexible pipe or if we're concerned about the pipe shape. And then finally at the bottom, medium or high resolution inline technology. So this is the more expensive electromagnetic tools or ultrasonic tools from the inside that can provide that really high resolution. So it's important that we think about the value of what we call the find and fix approach. We weigh that value against replacement. So when I say find and fix, that presumes that we're going to look at the total cost of the find and fix approach, which is finding the defects, whether we're finding them from the outside or the inside, and then we're following up with the repair or the rehabilitation after we find it. So that total cost should be weighed against just a straight replacement of the pipe. So when I say total cost, it includes 4 different elements of the find and fix process. The first is the inspection preparation. The second is the inspection support. Third is the inspection and condition assessment, which involves the engineering analysis and recommendations. And then finally, the repair and rehabilitation work itself. So with the first inspection prep, we're looking at the valves that are connected to the pipes, make sure they work. So we're not losing tools down laterals, or do we have valves that we can access to assess it from the outside, whether excavations are required. Sometimes new access points are required, and in some cases, cleaning before inspection. And then for the actual inspection support work, making sure that the utility has staff available for turning pumps on and off, manipulating flows. Sometimes this involves valve efforts. In some cases, doing shutdowns, addressing traffic control, as well as opening and closing flanges. Doing the inspection work itself, whether you're doing leak detection, structural pipe wall inspection, We've got to make sure that we're thinking about the verification process and the costs associated with verification. Some of these inspection tools are new and they require calibration. So we got to make sure that that verification and calibration work is included in the total cost of the project. Then finally, the engineering analysis and recommendations in terms of what to do once we find these pipe defects. And then the last one, repair and rehabilitation, thinking through what is the risk of repeat failures. If we know some of this damage, some of the leaks, some of the pipe wall weakening is undetectable, what is the risk of repeat failures, and what's required in terms of shutting it down to get these repairs or rehabilitation done, and then the design and construction management. We got to make sure this entire package is weighed against replacement. So for example, if you had a transmission main that was a new replacement pipe that the cost estimates showing it would cost about $10 million to replace it, then the find and fix process really shouldn't cost more than $1 million to $2 million. And this is about a 10 to 20% equivalent. And this is typically the threshold that I see working with utilities. Once you start to get above that 10 or 20% number, people would rather put that money towards replacement and get a new pipe rather than try to fix the old one. So one of the things that's important to acknowledge is that each pipeline's different. Each material fails differently, and it requires custom assessment techniques. There's no silver bullet that tells you everything you want to know about the pipe. So a lot of the pipes we see with big transmission mains are often PCCP or pre-stressed concrete cylinder pipe. We also see a lot of reinforced concrete pipe. A subtype of this is bar wrap concrete cylinder pipe, or BWP. We see a lot of steel pipe that's coated and lined with various materials, ductile iron pipe, cast iron pipe, PVC, HDPE, as well as asbestos cement. So once we understand what material we're dealing with, then that can help prescribe the specific type of inspection that's the most appropriate, and we're identifying the correct failure modes. One of the challenges that metallic pipes are built thinner today than in the past. And this chart on the left shows the pipe design thickness, the decrease over time of the same pipe. So this is an example of if you had a 36-inch diameter metallic pipe that was pressure rated for 150 psi, if you ordered that pipe in 1908, it's going to be a cast iron pipe that was pit cast, and the pipe wall is going to be 1.58 inches thick. If you ordered that pipe in 1952, it's going to be a spin cast pipe that's 1.22 inches thick. And as we move forward into the transition between cast iron to ductile iron in the 60s, and even the ductile iron today, it is a stronger metal, but it is thinner. And since corrosion doesn't care how thin your pipe is, corrosion's going to move through there quickly. Corrosion's going to move at the same rate. And so if the pipe is thinner, we're actually seeing some early failures with ductile iron that was installed in the 80s, 70s, and 80s. And so one of the main takeaways here is that age alone is a poor indicator of condition, and more studies are confirming this. When we're dealing with non-revenue water, they separate losses into two components, apparent loss and real losses. And so we'll talk about real losses here and the three different types of real losses. So the leak on the right, this is a leak that's surfacing. These leaks are usually reported either by your customers or utility operators. So these are the ones that surface and get reported, and they typically get fixed fairly quickly. Some of the leakage, the second type of leakage that AWWA provides this category for is unreported leakage. This is a leak that doesn't surface, but it is detectable using acoustic tools. And then finally, background leakage. So this leakage happens and it stays unreported and it's undetectable using acoustic equipment. And that's probably one of the ones that's the most notorious depending on where you are, what your situation is. One of the key things to note here is that this line between background leakage and unreported leakage, it moves depending on which tool you're using, as well as the skill of the operator, particularly if you're using acoustic tools. So what are some of the tools here? With reported leaks, one of the ways to address these is to have a process that allows you to fix it very quickly, to identify it and get it fixed quick in terms of reducing water loss. So just simply walking or driving the alignment, or having a call process where people call in and report these and you get them fixed quickly. With unreported leakage, this is where having a proactive leak detection program can be really helpful in reducing this non-revenue water. Oftentimes this leads to replacing services and mains. Most of the leakage tends to be on the near the services or valves, things we can see from the outside. One of the newer areas that's showing a lot of promise is just by reducing pressure by 3 to 5 psi. 3 to 5 psi can have a dramatic effect on reducing leakage. And then finally, with the background leakage, really the only tool here that may work is satellite leak detection. We're still evaluating the efficacy of that. There has been some success on using satellites to find background leakage, but there also have been numerous false positives that we're evaluating. But at least today, replacing services and mains can be very effective here when you do this, trying to reduce the number of joints and fittings, and as well as reducing pressure. So external leak detection is used a lot. It's a fantastic tool. We can find a lot of leaks, but sometimes we can miss these detectable leaks unless you touch the pipe often. So it's typically not a problem for some of the harder materials. So steel, cast iron, concrete, these are materials that facilitate really high transmission of the sound. So this chart shows a leak simulation in the center. So this is the leak that's happening, and this red line shows the sound wave and the distance traveled by that sound wave. So as you move into the softer materials, concrete and plastic pipe, that sound just isn't going to travel very far. So unless you're touching the pipe often, you might miss some of these detectable leaks, and that's where putting a tool in the pipe can be helpful in finding those leaks that are detectable, but not from the outside. So we can have a similar challenge in large pipes. So leak sounds simply just don't travel very far in large pipes, and this is due to the basic principle of sound absorption. So the bigger the surface area, the more sound is going to get absorbed. So if you're in that small 8-inch pipe, that sound can travel quite a long distance, but as you move into the 12s, 18s, and 24s, that sound just isn't going to travel very far. So this would be a good application, these larger pipes, for inline leak detection. A lot of the anecdotal evidence from different utilities we've worked with is approximately 30 to 50% of detectable leaks don't surface. Each one of these pictures are leaks that were found using inline leak detection because they were not surfacing and they could not be heard with correlators. So this is based on some recent leak data that's been collected. These are the average length of pipe that was inspected between leaks. And so on the vertical axis, these are the miles of pipe per leak, and for various pipe materials. So as you would expect, cast iron is the leakiest pipe. We see a 0.48 on cast iron. That's 0.48 miles per leak. So that means we're seeing about 2 leaks every mile, quite often in cast iron. Asbestos cement, we're going about 1.2 miles of pipe before we see a leak. Ductile iron, 1.5 miles between leaks. And then as we move to the right-hand side with pre-stressed concrete cylinder pipe, bar wrap pipe, the the leaks are much less frequent, with bar wrap being the highest at 4.8 miles between leaks. So this can kind of give you an idea of on average, what you expect to find doing leak detection work. Don't have a lot of time to dive into different rehabilitation technologies, but at least wanted to acknowledge them, and as a part of the important process of thinking through the total cost of find and fix. So the there's costs associated with shutdown and dewatering the pipeline. Sometimes we need to clean the pipeline before rehabilitation. AWWA has got a great manual, M28, that addresses a lot of these methods. Spray linings can be done inside of water mains, both non-structural and structural solutions, cured in place pipe as well. Various methods of pulling in new pipe, slip lining inside the old pipe. Then also thinking about reinstatement of laterals. This is a really hot area of research, and making sure that we can get a good connection to the residential areas back to that rehabilitated pipe. And then finally thinking through different ways to do disinfection, in some ways doing that quickly as well. But I'd be happy to answer further questions about that here towards the end. So just to wrap it up, in conclusion, pressure pipe assessment, while it's difficult, it can be worth it. Be sure to weigh the inspection technology against replacement. Hopefully we covered some of the quick, small tasks that can provide value that you can do yourself, or we'd be happy to help you with. And then thinking through how to start with that one critical transmission main, that one critical force main, and building a project for reducing risk as quickly as possible. So my email address is on the screen. Feel free to shoot me an email if you have further questions, but I think we've got time for questions.
Thank you so much, Andy. This is a very exciting topic with a lot of new, interesting technologies emerging all the time. Please do reach out to Andy if you have any further questions, or to your RJN primary contact.